Thank you so much for introduction. I will go directly to the talk. In the previous talk, Farzan mentioned to us what's happened to the matter when we are reaching cold temperatures, something like this. But in reality, we are right now at the room temperature, and the main point of this talk will be to answer the question how we can bridge this gap in temperature. And more explicitly, I will present you the methods for cold molasses and magneto-optical trap, which allows us to bridge this gap. Okay, and since invention of the laser, usage of the laser for heating of materials was kind of obvious because it has a lot of uh, photons with high energy. Therefore, it can translate energy to some materials, while the idea of using lasers for cooling of materials was not that obvious and only came in 1975, but already like in 20 years, the Nobel Prize was received for this topic by this brilliant scientist. And I will explain you today how it's working. And to do so, I have to introduce you some key concepts today. It's a concept of resonance, Doppler effect, and Zeeman effect. We will start with the resonance. As you know, the inside of our atoms, we have atoms and nucleus. And according to Bohr postulate, the atoms can only take, the electrons could only be on some stationary orbit. And to transfer from one orbit to another one, you need to absorb or emit some electromagnetic wave. And then this atom structure corresponds to some sort of energy diagrams. If we look on the bottom states with a lower energy, we can call one of the states ground state and the excited state excited. And what's interesting about the states that ground state is stationary, it's stable. When atom is there, it stays there for a long, long time. However, when atom is in the excited state, it doesn't stay there long, and it wants to emit photon as fast as possible to return back to the ground state. Energy gap between the states, we here note as a notion of frequency, omega 0. And imagine if you now have electromagnetic wave with a frequency of omega, then this wave will only interact with the atom if the frequency of those are approximately equal. Next notion is Doppler effect. I think most of us know it, and usually it's mentioned like if you have source which is radiate some wave and you have an observer, then depending on if source is moving and which direction it's moving, the observer receives the different frequency. And it could be understood by a typical example which all of us experience. When you stay and the car passes near you, initially you hear a high frequency noise when it's going towards you, but then you hear low frequency sound when it's going out. And as Sheldon said, it can be illustrated as meow, the sound which you usually see from the car, very, very fast moving car. And now we're good to move forward to slowing down atoms with the light. And let's now imagine that you have atom in the ground state which moves to the right. And then you have electromagnetic field which coming counter-propagating to atom. We imagine that this light is on resonance with atom, therefore it can be absorbed. During the absorption, as Farzan previously said, since the electromagnetic wave, both kind of particle as photon, as well as the wave, it can produce momentum kick on the atom, effectively resulting in the reduction of the velocity of the atom or momentum. Later on, since atom cannot stay longer in excited state, it will re-emit photon in some random direction and again receive momentum kick. If we average out over all these random momentum kicks due to emission and direct kicks from one direction due to absorption, we will end up with average zero contribution of the emission and positive contribution kind of towards cooling, towards slowing down from the absorption, which happens only from one direction. The same is true if atom the same but opposite is true if we consider atom which is moving to the to the left, and we have electromagnetic field which is co-propagate with atoms. In this case, all of those processes will effectively lead to heating up of the atoms, which show us that by just using one laser beam, you cannot cool down the atoms. Now let's consider the case that you have two counterpropagating laser beams, and we have atoms in between them. Okay, if these laser beams are detuned, it's called redshifted from resonance, meaning that it has a smaller frequency than resonance. In this case, if atom is not moving, the resonance condition is not satisfied. Therefore, atoms are not scattering any photons. They don't absorb radiation from the laser beams. They don't emit. Nothing happens. But now imagine that one of the atoms is moving to the right. In this case, the beam, which is co-propagating with atoms due to the Doppler effect, will be shifted even below resonance, even lower than it was previously, while the beam, which is counter-propagating to the atoms, will be shifted towards the resonance. Therefore, atom will absorb this laser beam more likely than the other one. As a result, it will receive momentum kick, which will be in the opposite direction of the propagation of the beam. You can imagine that the same will be true if atom will be moving to the left. In this case, you are receiving cooling in 1D. If you use this set of counter-propagating beams, but now in 3D, if you put this effectively 6 beams along x, y, z, then eventually you will get point on the intersection of this beam, and where atoms experience some sort of viscous force. And this technique was called optical molasses, because when atom goes to this intersection, they effectively experience the field, which is always trying to slow them down. And it works like molasses. And this technique allows to cool atoms down to approximately 100 microkelvins. And but what's interesting, you can see that this force is only have slowing down component. It doesn't have component which is responsible for trapping the atoms, because there is no dependence on the coordinate. There is no preferred point in space where atoms want to be. To understand how the trapping is working, we have to consider atomic level structure much more precisely. Previously, I said we have like electron states, these orbitals, but in reality, it's much, much more complicated. But the interesting thing which comes here is that there exist magnetic field sublevels which are degenerate. For example, for this case, we have 5 different sublevels. They are degenerate in the case when magnetic field is equal to 0, but they are have some energy splitting when we apply magnetic field. And this is energy splitting is proportional to magnetic number and the magnetic field applied. This is Zeeman effect. And why it's very interesting and fascinating is because effectively now you can change internal structure of the atoms by applying some external field. And this is, I found very fascinating. And now to move from different sublevels to other ones, you need not only satisfy the resonance conditions, but now you need also to satisfy selection rules. And what is saying that you can only change magnetic sublevel level on particular amount only if you have laser beam with particular polarization. What does it mean? That usually in our electromagnetic field, we have oscillating electric field and magnetic field. And we are saying that polarization of the beam is linear if electric component, for example, is only oscillating in one plane, while we call it circular if it oscillates, and if it oscillates kind of clockwise or anti-clockwise if it rotates in space. And yes, therefore, to do this transition, you need to satisfy conditions for your laser beams. And now we are ready to understand how Magneto-optical trap is working. The system quite similar. We still have circular, still have laser beams from both directions, but now they have particular polarization, and we have gradient magnetic field. The idea is more or less the same as for molasses, but previously we had some preferred direction, which of the beams we will absorb based on how close it is to resonance, and this how close to resonance was defined by the speed of atoms. Now it's still the same, but now the atom would prefer to scatter. The atom level structure is changing in the presence of magnetic field, and therefore previously a laser frequency was moving closer to resonance. Now, in some way, resonance or atomic level structure is moving closer to the beam. And if you imagine, for example, in this magnetic field where you have gradient component along z direction, positive here, negative here, your different magnetic sublevels will move up or down depending on the state. Therefore, for example, if you have atom which is on the positive z coordinate, it's with, again, redshifted laser beam, your radiation will be on resonance with the transition which corresponds to sigma minus transition, rather than it will be much off resonance for transition with sigma plus. Therefore, atom more likely will scatter this photon than this one, and it results effectively in the trapping force which we discussed, and it leads that atoms are want to be at the point of the zero magnetic field. This was 1D. In 3D, you can receive it again by combining 6 counter-propagating beams along all the 3 directions to cool them down in 3 directions and trap them, as well as 2 coils in anti-Helmholtz configuration, which creates the quadrupole magnetic field, and how it's usually done in the lab. This is the image for us. Effectively, we have a vacuum cell, and we have coils as well as laser beam, which allows us to create cold matter here in the middle. Yes, this is example how the cloud of cold atoms is look in our lab. You can see that the whole principle how we are trapping and cooling atoms rely on constant scattering of the photons. That's why exactly while they are getting cooled, you can already see it. And in our case, this is approximately like 1 billion of atoms, rubidium-87. And that's why you can see it. This is more or less how experimental setup for doing it looks. And here it's like real time, not real, it's video. And you can see that it's fluctuating a little bit, it's breathing because of different fluctuations of magnetic field in the room, like laser power and so on and so on. And what I will tell you next, that for us in our experiment, this is just the first step, which allows to do much cooler science later on. In our case, we are using this cloud of cold atoms to later on load an array of single atoms. And here you can see this is effectively each image is single experimental realization. And you see when you see bright spot, it means that you see single atom. And we are loading them stochastically, and you can see that it's every time different. Using this array of atoms, you can work and build quantum simulation. You can study. This platform is very wide in the sense, in terms of scientific application, and you can do simulation of many body physics. You can do quantum computation, quantum sensing, and metrology. And to do all of this effectively, much larger apparatus is required. And what I told you today is just very small part, which is located here. And to do much more interesting stuff, you need much more techniques, but all of them are very interesting. And if it's also interesting for you, please feel free to join our lab, and you can find all information here. And on this, thank you for attention. I'm happy to answer.
Thank you so much for that wonderful talk. Does anyone have questions? Please raise your hand. We'll pass you them.
There is.
Earlier when you were talking about like trapping the atom or like ion, I'm like a little confused on why we need like 6 like different like polarizers. Because I was just thinking like if it's already like stuck between like 2 polarizers where like magnetic fields and it's like an equal force on like both sides, wouldn't it be stuck there like already with like just 2?
Yeah, that's a very good question. Let me quickly return. maybe even here. Yeah, more or less you were saying that since we already have trapping force along one direction, but in this case, as you can see, imagine that you can only confine atoms along here z direction. Nothing prevents atom to move here, to leave it from the side. Therefore, you need to make sure that this trapping force works from all directions, as well as the same as cooling force.
But like if nothing's acting on it in like the x direction or like the other directions, then like it doesn't have like a force to cause like acceleration in that direction anyways.
In general, yes. I think that there will be still small cross coupling, because if you imagine, it's very difficult to imagine experimentally system where you have gradient only along one direction, because I think it's impossible. You have to have like your magnetic field should cross the line. Therefore, you always would have this magnetic field, which is kind of, if you have some component along x, then you would expect that it will kind of close the loop. But eventually, for quadrupole magnetic field, you will have still some force. But indeed, sometimes, for example, due to some experimental constraints, you'd not necessarily need to trap atoms at one point. You can afford to be trapped stronger in one direction and much less strong in another direction. It will still be sufficient, but indeed, it's like effectively in first approximation, you don't have force along different direction if you don't have their magnetic field or beams.
Okay. Yeah, right. Thank you.
Maybe one more question
There is right here.
Thank you so much. I was just wondering if that experimental setup can trap the atom indefinitely, or is there like a time limit to how long you can keep that atom there for experiments?
Yeah, that's a very good question. I would say there is few different traps in our setup. One is what I described, magneto-optical trap. And here, in reality, we would like to have it as short as possible, because it takes a lot of time to cool these atoms down. But for us, it's only important to create this initial medium from where we later on will load our single atoms. Therefore, we want to reduce this time as short as possible. But in reality, if we would like to hold it, I think that there is always like atoms still moving there. There is atoms still scatter photons. Therefore, effectively, an atom also experience, although we are working in the vacuum, atoms are still experience the collision with the background atoms inside or molecules inside the vacuum chamber, which effectively leads to atoms leaving the area. But if you have constant sort, the idea that if you trap them and then you don't have input atoms anymore, sort of, for example, you trap them and you don't have source of the atoms coming in, over time they decay. But for example, in our exactly single atoms, it's also limited to around like milliseconds, because these atoms which we see here, maybe seconds actually, atoms which you see here, they are trapped using tightly focused laser beam. And it's off resonance trapping kind of, but atoms are still, although it's far from resonance, due to high intensity, there is always chance that atom will scatter photon, and therefore this scattering of photons effectively leads to the heating induced by this dipole trap, small traps. Therefore, effectively, it's always balanced that there exist processes due to like fluctuating magnetic fields, changing of intensity, some not constant rate of scattering, which leads to the heating. And your task as experimentalist is balance them out and to receive the best performance in some way.